Hello guys, welcome back. So today, this video is going to be more or less of a continuation of the last video of organic reactions for certain compounds. For the standard levels, we already discussed quite a lot, and for the higher levels, you're expected to know even more both reaction mechanisms and types of reactions overall. So the new ones that you'll be doing, you'll be studying a lot on nucleophilic substitution, electrophilic addition, and substitution, and partial reduction reactions are new this year, but they are essentially the opposite of the partial oxidation reactions that you studied before. So here's sort of a map of what you'll be covering. This is sort of a roadmap of where you're going to be expected to be going. You're expected to memorize all of this. So I think the first thing I want to cover are nucleophilic substitutions, because there's a lot of new information that you're expected to know for the higher level syllabus. A nucleophile formally is defined as an electron-rich species capable of donating a pair of electrons to an electron-deficient species. Nucleophiles are nucleus-seeking agents, and nucleophile, literally breaking the word down, nucleo meaning nucleus, and philic meaning affinity for, so affinity for nucleus, whereas an electrophile is just that, electro referring to electron, philic again meaning affinity for, so affinity for electrons, and these are generally positively charged molecules, whereas those nucleophiles are generally negatively charged ions compared to positively charged ions. Lastly, nucleophiles generally are Lewis bases. They donate their electron lone pair, whereas electrophiles are Lewis acids. They accept an electron pair from another molecule. So to be a nucleophile, there must be a lone pair, and so that it's capable of being a Lewis base. And generally, if it's polar, generally the higher the negative charge, the stronger the nucleophile is. So there are two possible mechanisms for nucleophilic substitution, and this again depends on the degree of the halogene alkane. Typically, you'll see this under the context of halogene alkanes becoming alcohols, but you don't necessarily have to. But primary halogene alkanes will undergo Sn2 or substitution nucleophilic, and the 2 refers to the fact that it is a bimolecular reaction. It is bimolecular, and Sn1, the mechanism is bimolecular, and then tertiary molecules will undergo Sn1, which means that it is which Sn meaning substitution nucleophilic, and the 1 referring to the fact that that particular mechanism is unimolecular. Sn2 reactions are second order reactions. They involve 1 steps, however that elementary reaction is bimolecular. This type of reaction occurs because the polarity of the carbon halogen bond is polar, it's highly polar, and therefore the nucleophile can attack the partially positive end of that bond. And when bromomethane is heated with a concentrated solution of sodium hydroxide, the halogen atom is replaced by a hydroxyl group. And the rate law is shown below for this second order reaction. Note that it's overall second order because the rate is equal to K times the halogene alkane concentration times the hydroxide concentration. Both are the overall order is 2, but each reactant's order is 1. And this is something you're expected to memorize. And for nucleophilic substitution reactions by the Sn2 mechanism, the rate of reaction depends on both the halogene alkane and the hydroxide ion. Again, nothing we couldn't deduce from that. The Sn1 mechanism is slightly different. It involves 2 steps. Step 1 is a unimolecular elementary reaction, and it is also the rate determining step. So the first step is basically the halogen breaks off, and then the second step is the alcohol comes in. So Sn2, it just sort of happened all at one go. So the nucleophile displaced the bromine, displaced the halogen, whereas in an Sn1 reaction, it's clear that the halogen leaves and then the alcohol comes in. the hydroxyl comes in. So it involves two steps, and the overall rate law is this: just K times the concentration of the halogene alkane. You're expected to know why certain halogene alkanes will undergo certain mechanisms, and there are some factors you want to consider. Um, you want to consider carbocation stability and steric hindrance. Those are the main reasons why. Carbocation stability, basically, third degree carbocations are more stable than second degree, which are more stable than first degree carbon cations because of something known as the inductive effect. Um, basically, basically what it amounts to is that the C plus carbon 1 plus is very unstable, but because carbon 1 plus is stable and more electronegative than neutral carbon. Therefore, if you have more hydrocarbon chains attached to it, there are more electrons total, and that highly electronegative carbon can essentially pull electrons toward itself, sort of stabilizing it. Whereas first degree carbocations, well, they don't have nearly as many electrons since there's not enough hydrocarbon chains attached to it. Therefore, since there's no electrons to really pull in, it's less stable. And then second degree carbocations are somewhere in the middle. They have some electrons they can pull towards itself, but not enough to make it as stable as a third degree carbocation. This means that third degree halogene alkanes are stable. They form stable enough carbocations to react by the Sn1 mechanism. Now, steric hindrance is basically a formal name for how bulky the molecule is. Now, having these large, bulky hydrocarbon chains attached to a carbon of interest with the halogene alkane, they take up a lot of space, and therefore it means that the nucleophile can't really attack, because it's blocked on both corners. It's like having a shield, and the nucleophile can't really attack through the shield. Whereas first degree halogene alkanes, while those hydrogen atoms are tiny, and therefore there's less of a shield protecting the halogen from being displaced. So therefore, first degree halogene alkanes will undergo SN2 because there is minimal steric hindrance, and they also don't form stable enough carbocations, whereas third degree halogene alkanes are generally stable enough to form stable enough carbocations to exist for however long they need to exist before the alcohol binds into place. And in addition, there's too much steric hindrance for the hydroxyl group to displace the halogen, since they're too bulky. So that I sort of discussed. Rates. Some factors that affect the rate of nucleophilic substitution are the type of halogene alkane. For some reason, Sn1 reactions are faster, which it makes no sense since, okay, you would think Sn2 second order is faster. In reality, it's not quite this way. This trend is kind of stupid. The IB expects, teachers to teach it, so therefore I have to say that Sn1 reactions are faster than Sn2, but in reality, this actually depends on a lot of things. However, one thing that is consistent is that the identity of the halogen, where basically the weaker the carbon halogen bond, the faster it'll react. And this makes sense, right? Since the activation energy is lower, more particles will meet the activation energy, and therefore the reaction will be much faster. The exception to this are carbon-fluorine bonds are so strong to the point where they just don't undergo substitution. And then lastly, the type of solvent used does affect the rate of reaction. Protic solvents basically allow Sn1 reactions to go faster because protic polar solvents basically allow the inductive effect of the carbocation to really maximize across a large range of space, and it can pull more and more electrons to itself with those protic polar solvents to help stabilize it. Between solvent ion interactions, solvent ion interactions solvent ion interactions help stabilize third degree carbocations, and therefore polar protic solvents work best for Sn1 reactions, whereas aprotic solvents work best for Sn2 reactions because they aren't capable of hydrogen bonding, whereas those polar protic solvents are, capable of hydrogen bonding, and therefore they they basically make it such that even if it was possible, even if the basically they make it impossible for carbocations to form, and then so if something already favors Sn2 and you make it not favor Sn1 by adding a non-protic polar solvent, it'll go via Sn2, and therefore the Sn2 mechanism is even more favored, and therefore it'll be faster, I guess is the way to explain it. The last thing that is expected of you to know for nucleophilic substitution reactions is that Sn2 reactions are stereospecific. With an inversion of the configuration, basically you go from a left-handed molecule to a right-handed product, and this is formally known as the Walden inversion. The Sn1 reaction mechanism is not stereospecific. So there's that. The next major type of reaction that you're expected to know is the electrophilic addition reaction, which basically we studied this in the context of addition reactions of hydrogen, halogens, water, and hydrogen halides, but now you're going to be considering interhalogens, which are compounds composed of different types of halogens, so BrCl, and you'll be introduced to addition reactions for non-symmetric alkanes, and this is where we come into Markovnikov's rule. Basically, it states that when a hydrogen halide, HX, is attached to an asymmetrical alkane, the hydrogen atom will preferentially bond to the double bonded carbon that contains more hydrogen atoms. And you can generalize this rule to that the least electronegative atom will go to the carbon with the most hydrogens, because hydrogen is a very low it's the lowest non-metal it's the non-metal with the lowest electronegativity. So therefore, things that behave like hydrogen, so things that have lower electronegativities, will generally like to group with hydrogens because they sort of play around nicer because they are of low electronegativities, and since they're so similar to each other, it's just easier for that. It's just easier for the lower electronegative element with lower electronegativity to bond to the carbon with more hydrogens to it. And the formalism for that is, okay, so here's the mechanism. This bond here will attach to this slightly positive. Remember that hydrogen halides are polar, so this will have a slightly positive end, slightly negative end, and the slightly positive end will be attracted to the electrons here in this double bond, and it'll form a carbocation. And remember, if it was forming here, you would get a first degree carbocation, but if it forms here, you get a second degree carbocation. And as we discussed, the second degree carbocation is more stable because of those inductive effects. And then the bromine will just snap on there, and ta-da, you get a halogene alkane. Another way you can think in Markovnikov's rule is, I don't like this way, but I'll teach it anyway. I'll say it anyway. When an asymmetrical molecule is attached to an asymmetrical alkane, the favored product is the one where the more electronegative element is attached to the more substituted carbon, and the less electronegative element is attached to a less substituted carbon. I prefer to think of it in terms of hydrogens, that the less electronegative element will go to the one with more hydrogens, because hydrogen is low electronegativity, and basically it behaves like hydrogen. It behaves like an adopted hydrogen, more or less, to put it that way. For some reason, you're expected to know this. Now we revisit again that benzene undergoes electrophilic substitution, and you're expected to know the full mechanism for the nitration of benzene. The overall reaction is this: if you add nitric acid to benzene, you get you get nitrobenzene plus water. This is the mechanism for the reaction that you're expected to know. I'm not going to cover it in detail. I'm just going to breeze through this part because this is mostly just memorizing. Firstly, you use sulfuric acid to protonate nitric acid, and once you protonate nitric acid, water will break off, and then you get an electrophile, and then the electrophile will attack the benzene ring, and it will displace a hydrogen, and therefore it'll displace a hydrogen. And that displaced hydrogen goes back to the sulfuric acid, which is the catalyst for this reaction, and you get nitrobenzene. That's really all there is to it. Lastly, we consider reduction reactions, which are basically the opposite of those partial oxidation reactions, and you can use reducing agents such as lithium aluminum borohydride and sodium borohydride. The only catch is that sodium borohydride will not reduce carboxylic acids, it will not reduce carboxylic acids. So ketones can be reduced to secondary alcohols, carboxylic acids and aldehydes can be reduced to first degree alcohols, and you can't really reduce tertiary alcohols since they never reacted in the first place. Lastly, we go back to visiting nitrobenzene. Once you have nitrobenzene, you can convert it into phenylamine, which is another reduction reaction, via two steps. The first step involves zinc and concentrated hydrochloric acid to form the phenylammonium ion, and then you can use a simple acid-base reaction with NaOH to form phenylamine and water. Since this is an acid, this is a base, and you get a salt. Well, technically, this is a salt, I guess, and a water. It's not really a salt, but you get water formed as a result of it. Using all that, the culmination of all this is organic synthesis, which is the study of retrosynthesis, which is basically you have something, how do you turn it into something else? And basically the way you go about that is you start at that something else and you consider the functional groups it has, and you think, okay, how can I go, and then you sort of work your way backwards. Okay, so I know oxidizing something else will get you this, so what if we did that? So what if we consider that as our last step, and then okay, I know adding something will get me to that thing that I know that if I oxidize it, I can get that, and you can sort of repeat this backward process over and over again, and then you will eventually get a way to turn the thing you have into the thing you want. I think that's all for today. Thank you very much. Don't forget to like and subscribe.